Uh, I think it's time for me to ask the student to come with this kind of a project. Again, I told you in the beginning we have no final exam, but I do want you to think about how to work on some project on vibration engineering, so that and you can also actually, if you look at our website, our campus website, we do have give you some example about this kind of project you may want to consider to some practical vibration engineering. For example, this is just give you one template for you to think about what you can think about to make some project, right? Of course, if you have your own idea, no problem. If you don't have your idea or thing, I can also come with some recommendation for you to consider about this kind of project, huh? And of course, so I told you, vibration engineering has many applications, so that it's really up to you to think about what kind of project you want to do, huh? And of course, in the past, if you want to work practical, I can also ask our Yunzhou Tech to give you some project related to their company's vibration engineering thing. So what do you think? You prefer to have some more the project with some company relating, or you want to come with your own idea? That's also fine, huh? Do you any idea about the project you want to do? Huh? Any? At least I told you this in the past, some students they can come with their own project. Some students they may want to do something different, huh? So that Yunzhou Tech is one of our students, huh? Key student who the company now is become, do you know how big the company? Huh? It's about 600 people now. Huh? Anything you want to work on some project related to some company or thing? What do you think? Huh? Hello? I want to ask if you want to come your own idea, or you want to work on some project like related to some company like this Yunzhou Tech. Because I know the founder and CEO, he's actually our student graduate, huh? He's 600 people, huh, in his company. And I know that they intend to do IPO, become public company. So that, what do you think? You can look at the introduction of their Yunzhou Tech, right? So it's really, I think, quite impressive. So that they really do a good job. Huh? This company will make a good job and then he has so many products, huh? What do you think? You think you want to work on some this kind of company project, huh? Oh, in the beginning, the first prototype he made here on campus, electrical this amazing ship for water pollution, and then he quit his PhD program and then start a company. Now he has 600 people. Huh? Mr. Zhang Zhang Yuzhou is a pretty big boss now. 600 people, and it's pretty impressive. He has so many products, and then so originally it's only for pollution, right? Then you have a lot more this kind of thing. It's quite amazing to see that our students can really make a very good job. For if you look at they do have very impressive this kind of thing in Yunzhou Tech. No, it's maybe quickly show one of their introduction.
Leading Drone-Tech Unmanned Surface Vehicle, USV, is a robotic platform for automatic operation on water with autonomous navigation and intelligent obstacle avoidance. In Drone-Tech USV is made of high-strength fiberglass and carbon fiber. All of this the cruising speed is 1 to 5 meters per second. The maximum endurance up to 100 kilometers and communication range up to 10 kilometers. Users can set up mission in base station software. USV works autonomously. Meanwhile, real-time data and monitoring video can be received on the base station. Drone-Tech USV offers an innovative solution for water environmental monitoring, hydrology measurement, and hydrographic survey, etc. The water sampling and monitoring boat is able to collect water samples automatically and monitor online water quality. Software can output water quality parameters, contour map, and track pollution source. Water surface cleaning boat can collect floating garbage on water. The hydrographic survey boat is designed for automatic underwater survey and mapping. Greatly increases the survey accuracy and efficiency of traditional operation. The industry leader, USV, will continuously dedicate safety.
Well, what do you think? Do you want to do something related to this kind of company project? I do can talk to the CEO and then ask if they have some ongoing new project for this for the product. What do you think? Anyway, so it's something up to you, but at least of course we do have. If you look at this reference, and then so that we do have some students come with their own idea for the project. I still remember we do have some students come with their own idea for the project. It's something of course, if you want, then I think we can discuss, right, to see if you want to do, okay? Okay, so that if no, then I think we need to continue our lecture. We already discussed about this multi-degree of freedom system, and then we have talked about how to use this kind of method to get this kind of MCK, right? For multiple degree of system, and then of course we also show you about this the how to use. Sorry, maybe I should copy. So at this moment, we already talk about how can we build undegree freedom system using the Newton's law, right? But if Newton's law has now limitation, it's too complicated if n become so big, right? So that then we look at flexibility inference coefficient and stiffness inference coefficient, right? To this is another approach to redefine our Kij, stiffness inference coefficient, and also this kind of Aij, right? So that I will show you here. Of course, we will show you about some example. How can we really use, for example, vibration of the beam, right? So that how vibration of beam has a degree of freedom go to infinity, right? So that can we use 3D freedom system to the right thing, right? So that's something is, of course, now the question now is, can we try to think about some more generalized way to analyze this kind of vibration problem, right? That means if we have undegree freedom, MCK, right, system, mechanical system, MK, So of course, we may try to just simply define each mass with certain kind of energy, kinetic energy, 1/2 mv squared, m1 and 1, 2. So and also we also have each spring with a certain kind of kinetic energy stored in the spring, and then summation. Then we can also simply so I should share this thing. Then we can so the summation of this energy, right? So we have n degree freedom system with n masses m1, m2, and n, and the spring, and then so that the sorry, I think we need to think about, and then of course in general we can try to write down this kind of if there's no damping, and then we'll consider n degree freedom, right? Mass spring system in terms of ODE system, right? So this n is what? N by n matrix, right? And this is something we'll show you how we can get these kind of matrices, right? And then next one is how can we solve this problem under harmonic vibration? So of course, we can reduce this kind of ODE system, order differential equation system, into the differential simplified linear algebraic equation. So that one simple way is we'll soon generalize solution, right? And then so that for each mass x1, mass 1 we have x1 a function of time multiplied by a capital X, this vector, and then t. Capital T is a time-dependent function. This is a vibration amplitude vector, right? So each m1 we have certain kind of x1, m2 we have x2, right? So that this is a general solution, and then we substitute into our equation of motion. Eventually, we do separation of variable, right? And finally, what we have, actually, we can rearrange this complicated equation, and eventually we can move all the term related to the time-dependent term, capital T function, and the other is here. Eventually, left-hand side is independent of I. Right-hand side, we independent of time. So in this case, in order to satisfy this kind of rearrangement, basically it is a simplified equation of motion, Newton's law. But in this way, because we make assumption xi equals this t, so we can simplify, right? Simplify this kind of distance. So this is basically this is a Newton's law in simplified form, right? In order to satisfy them, then this one can only become what? A constant. Okay, so that because in this case, so this constant we can assume to be omega squared. Okay, so that in this case we arrange, we find left-hand side, we find one equation for this time-dependent function, right? And of course, all of you have no problem, right? This is second order ODE, so the general solution is this, right? And then so that that is something I think all of you have no problem to understand this thing. The same thing on the right-hand side, we have another equation, right? That is related to what? Eigenvalue problem. So that eventually this is the matrix K mat omega square m multiply this kind of vibration amplitude vectors for basically this x1, x2, xn vector. Right? So this n by n. So that in order to get this solution, so that this cannot be zero, only this one matrix can be zero. So then we eventually we let this one to be zero. Right? So the only thing you do is now the determinant of this matrix should be zero. And finally, so this is exactly what we learned by eigenvalue problem. You learn this kind of linear algebra. right? And then so that omega square is eigenvalue. So I think this is officially we can use this kind of way to reduce. Again, the key thing here is under this kind of free vibration, there's no harmonic force applied. So free vibration, our equation of motion can reduce into this kind of eigenvalue problem. So this is a important thing. Let me write down. So that means for this kind of free vibration, let me external force, right, is zero. So this condition, then our equation of motion, right? Equation of motion will be reduced what? Complicate equation of motion will be its ODE will be what? Become this kind of linear algebraic equation, linear algebraic equation. Why? Actually, this is eigenvalue problem. So that this is one of important thing. And of course, we will show you how to solve this kind of eigenvalue problem. 1 degree freedom, 2 degree freedom, and even n degree freedom problem is become the piece of cake if using the what? MATLAB. We will show you about MATLAB, right, to solve this kind of eigenvalue problem, right? So what kind of MATLAB function can you use? You remember? EIG, right? I will show you this kind of EIG, and so that basically, so that with MATLAB is a piece of cake now. It's so simple, right? So basically, you can use EIG, it's MATLAB the function, right? EIG, and then try to solve this one subroutine, right? To get this kind of the omega natural frequency, omega, and also vibration mode. Okay, so this is something we'll describe. Of course, I think we sometimes as I show you in our previous example, in the MATLAB, we try to rearrange our eigenvalue problem by multiply both sides by this inverse of K matrix. In this case, we can easily simplify into this kind of a very simple eigenvalue. Our D is called a dynamical matrix, right? So that is something we will show you in our previous example. But then, what's the important thing? Of course, here, I think we already show you this example. I will skip this part, right? Maybe I quickly repeat this thing. Right, so this is the problem we have solved. Let me try to use MATLAB now. Basically, let me quickly show you an example. Right? For this 3D freedom problem, why? If we know this kind of MCK, and then how can we try to use MATLAB? So we already have this kind of, let me quickly. Okay, so for this example, basically, we know we get all the mass and stiffness, right? K1, K2, K3 equals K, and M1, M2, and 3. So in this case, with MATLAB, we can easily try to build this kind of K and M, right? So that is very easy now. So that with MATLAB, I just show you that we can easily find our M and K, right? And then next one is of course we try to do what? Using this kind of EIG. get the dynamical matrix. Huh? We calculate our dynamic matrix, right? Inverse of K multiplied by M, and then use this EIG to determine our VV and DD. Why? VV is related to the what? You stack this kind of eigen vector, right? So that this one is related to the eigenvalue omega square. So that I think we already described this one. Oh, sorry. Sorry, I should see. So basically, we already show you about how we can use MATLAB to receive, right, so that we can calculate VV. VV basically is the stack of this kind of vibration. VV basically is a I don't know if I share this one. So let me quickly describe, right? So this one basically is related to the first, right? Eigenvectors, eigen vibration mode, second, and then of course for each one we have what? Corresponding omega square. So DD relate to the omega square. You see, for this one, omega 1 square relate to this vibration mode. Omega 2 square is what? Omega 3 square. Okay, so this is something I think we already described this before. So what's the next step? Huh? Next step, of course, is try to calculate omega, right? And also vibration mode. So basically, we have the lambda. Lambda equal diagonal D. So see, because DD is this kind of diagonal matrix, right? So DIAG means just collect this one, this one, this one, become here. Okay. And then next one is calculate omega. Remember, because omega is what? Related to the inverse of lambda. Okay. You look at the equation with the right, so that that is our here. Dynamic matrix here, so that lambda equals 1 omega square. Okay, so that in this case we can find our omega equals in square of inverse of lambda. Remember this one period, this one, because this is a vector, this is the one. So that when you do this one, if you don't have this one, then you get some problem error. Okay, so that this if you use this guy, then you problem. If you don't use this one period and then whatever, you see, it's not correct. So we want to divide by each component of lambda vectors, so that in this case we can get the right solution here. Okay, so this is our omega. Actually, it's related to omega square. So we need to do square root of this kind. Sorry, so that if you look carefully, so that we need to use this kind of square root. You see, so square root, right? Square root of this one square root, right? So this become omega, and then of course the next one is we can collect those here. V1, VV is a stack of 3 vibration mode, right? So this means we try to collect the first, right? Basically VV here. Right, so basically we have a X1, X2, X3, right? So that in this case we try to collect this one, so that we basically is we try to see, okay, find the first color. This means first color. One, first column of this VV matrix, and then this one second column, and 3, 3, 3 here, third column. Okay, so that in this case we can get the vibration mode for V1 for first omega 1, V2 omega 2, V3 omega 3. So this is the one we can use MATLAB to calculate it. And finally, what's the next step? We should plot this kind of response. Do that. You want to look at the vibration mode, right, as function, so that eventually what we'll do is we try to think about how can we get this kind of vibration mode. Our goal is to try to study this kind of vibration mode, doing that. So that we show here, then actually I already try to, I will plot this one. Let me quickly. And then of course, actually, I already tell you that the MATLAB can try to plot this kind of vibration. Okay. Sorry. There's a way we can try to do this kind of to place this kind of vibration now as a function of time, so that I hope still remember, so that basically for each vibration mode is function of what? Function of sine omega t. So that once you find each vibration mode, and then in reality, each vibration is what? Your x1 is actually multiplied by some kind of harmonic function. So each x1 basically relate to what? Some kind of sine omega t harmonic at that particular frequency, omega 1. Why x2 vibration mode 2 equal maybe sine omega 2. So that you can also ask MATLAB to try to plot this kind of time-dependent vibration of this kind of 3D feeder model for your mechanical system. So that in this case, here I show you that we can use this kind of thing to, you see, for each like vibration amplitude vectors equals this one, vibration mode and sine omega t, so that we can plot this one, and then for every time we plot this particular moment, and then we can make a movie to show this kind of vibration as function of time. So that I don't know, do you still remember how we show it? Basically, this is the way we can make this kind of animation to visualize vibration as function of time. Let me, do you have any question about this thing? MATLAB is useful. Let me quite quickly show you this. Right. So there's some problem. Oh, sorry. When I plot this one, I understand. You know that we may need to. Let me check if I need to. So do you understand what's the problem? Problem is this one. Sometimes we need to use this kind of let's try to copy. Okay, typically you may want to write the M file. This is a MATLAB program. I set this as M. I just create this. Oh, eh? CDOFNK, why did not work? Eh? Oh, let me see what happened. See? I try to do the animation of the first vibration mode. Do you have any question? Huh? We can see visualize the second vibration mode, right? Using the same chip, basically, second vibration, basically you need to get another V2, right? You use the V2 and then try to plot V1, V2, V3, so that we can do the same thing. Vibration 2. So this spatial natural frequency, they have this kind of vibration mode. And then next one is another. Finally, we have another vibration mode, right? V1, V2, V3. So that all the other is the same method. You just try to. I probably can go. So I have V3 and then another V2. So now I show you the number 3 vibration mode. Any question? Of course, this is the one 3D freedom, right? So that in reality, if you have a more freedom, then you can process more complicated vibration of mechanical system. Huh? More complicated. Yeah. If you earn, this is on 3D freedom. Okay. Okay, so I think this is give you this kind of introduction about how we can use MATLAB to sorry. So now the next question is I need to show you another important property, orthogonality of a vibration or normal mode. Sometimes we call this is another name. Sometimes we call the vibration mode, right? Huh? Or normal mode. Vibration mode. We just show you right? And over sometimes it's actually related to the eigenvector. Eigenvector. We just described here in a MATLAB. So what's the meaning of this orthogonality of this vibration mode? It means we can demonstrate this kind of. I will not show you all mathematics. I just show you the idea. Actually, for each this kind of a vibration mode or normal mode, they're useful to what? Basically, I show you why. In MATLAB, will show you this kind of x1, x2, and x3. Why? So this kind of vibration mode or normal mode, they have their spatial property to orthogonal. Orthogonal is perpendicular to each other with respect to the k and m. Okay, so this is, that means vibration mode, this is vector and this vector. So x vector is perpendicular to x2 with respect to our n and k. So that thing is quite important. And x3 is another x3 is also perpendicular to all the things. So that this is a very important property, orthogonal, with respect to m and k. Because this kind of property, so I will not just show this common mathematics, but the reality is not this. The result is very important. Why is it important? This is probably show you that if number omega-1 square is not equal to omega-2 square, in this case, this kind of you see vibration mode J and multiplied here, and then equals 0. This means they are perpendicular to each other, right? Based on our linear algebra. So that means Xj is perpendicular to Si with respect to this matrix here. Okay, so this is we call the orthogonal. Okay, so that the same thing. So this is quite important. Why this is important? Because we can simplify. If n is 2 or 3, that's simple. If our n degree freedom, n go to 1,000, 10,000, or 1 million, then this will be very complicated problem. So that orthogonality can help us to simplify our n degree freedom to much simpler, smaller degree freedom. Now we can solve in more practical way for vibration engineering. So that this is I just show the important thing here is this is a tool, right? Basically, this kind of function, this kind of property, right, can help to simplify, engineer our vibration problem. Okay. Now, when n go to become very big, right? For example, if n go to 1 million, if it's 1 million and then 100,000 or 1 million and then then can we use smaller number of n freedom to describe this kind of very complicated mechanical system vibration, right? So this is something I will show you. This is something is a practical approach. And approach. So this property will lead us to do now. Anyway, I just show you that of course we define this kind of thing. Actually, we already calculate in the MATLAB. Right? So basically, this is related to what model matrix is related to what we remember our V, VV, and DD in MATLAB. Well, eigenvalue here, so that it's basically is what we just described. It's a model matrix. And each one is model vector. So with this kind of property, so that we can really try to simplify our problem. Of course, we can show you, right? This kind of orthogonality of our previous one. That is very easy to show Now they are really orthogonal. Huh? Do you say? And then again, the most important result is we can really demonstrate that I will skip this kind of complicated mathematics. The goal is simple. So with this kind of once we have find this kind of natural frequency, eigenvalue, eigenvector, vibration mode, and then our undefined freedom vibration problem can be simplified, right? As this kind of thing. So let me show you here. Vibration of MK using the model analysis, so that if you don't do this kind of to solve this kind of vibration mode frequency and thing, then it's very complicated. We solve undefined problem. Model analysis basically is a tool we can simplify our problem. For example, I show here the result is clear, so that for undefined freedom, right, and then this vector basically is x1, x2, a function of time, and Sn, n can be 1 minute, right? Basically, it's what? It's a summation of n. This is the vibration mode 1 and Q1, vibration mode 2, Q2 function, and you can multiply this one. So basically, this is the model matrix multiplied by Q vector. So that this is the general solution. So that with this our model analysis, I show you that basically we can really now reduce undefined freedom problem into what? And into this kind of we have an one degree freedom model. So this is our goal. You see, if we can use this kind of model matrix and then try to simplify our already very complicated equation motion, Newton's law, right? And then so that do this kind of transformation. Originally is very complicated. It's an ODE system, and then with this kind of model matrix, that is a 3 multiplied by model matrix transpose, and then normalize the vibration mode, and eventually I can do transformation so that the NODE system will become an 1 degree freedom, 1 DOF thing. So each Q1 relate to the maybe 1 vibration mode, and Q2 relate to that means we have a Q1, Q2 for each kind of a model, maybe omega 1, omega 2, you say. So that means in this case we have one degree freedom problem. That is our important thing, and of course for each vibration mode as function of time, actually we can have a simple exact solution here, so that each one vibration mode, and we have this kind of solution for the from initial condition, initial displacement, initial velocity, and then this one is related to the force vibration. If additional forcing function on the first each vibration mode, and this is the free vibration, this is the force vibration. Okay, so once we get the solution for each vibration mode, Q1, Q2, Q3, then we can do transformation again, right? And eventually, our vibration for each mass, M1, M2, M3, we can actually, basically this is we try to easily do the transformation again. So you see, we basically, once we get a solution for each vibration mode and function of time, and then we can easily now determine this kind of vibration for each M1, M2, M3. Okay, so that is the quite important thing. So that with this kind of model matrix is it's clear. I will show you that based on intrinsic property or mass metric and K-set metric, so eventually we only use what? very small number of vibration mode is enough to describe very complicated mechanical system and product. So this is one of the important things. Model analysis is very practical for us to simplify our practical vibration engineering problem. So we don't need to use N. Probably typically say maybe 3 to 5 vibration mode would be enough to get the reasonable estimation of the real vibration of a mechanical system. So that this is something is important for all you to think about. Okay, and of course, if we have actually we can show you. Let me quickly show you some example. So model analysis for this kind of the problem we describe, right? For each, we will show you about that 3D freedom system M and K, and then basically, actually, if you use this kind of model analysis, you can really try to do converging of simplify you see N and K. That here I show you why we have determined vibration mode, 3 vibration mode, and then we stack this kind of each vibration mode into the model matrix, right? Vibration mode 1, 2, 3, and then MK. Then with this kind of what we describe, right? So more transpose of model matrix about MX. In this case, we can really get you can see this thing, right? So that we can simplify our vibration, this original very complicated system. The same thing, now we can also show you, you see, if you also gonality of this 2 vibration mode, vibration mode 1, and then multiply this K matrix and K vibration mode 2, you calculate eventually is almost 0. So this to tell you that they are orthogonal, and I show you that each vibration mode, they are orthogonal to each other, right? This is kind of like X1 and this X2. They are S2, so that in this case they are 0. Just like what you learn in this kind of simple vector analysis, right? But this is related to this matrix, to the calculation. The same thing, X1 is also orthogonal to S3. These vectors. Okay, so do you understand? This is something quite important property of this kind of model analysis. And then eventually, once you do this one, of course, you see, we can really try to do transformation with this kind of model matrix. We can transform origin C into what? Diagonal. This has become quite important. Diagonal matrix. So that would be important thing for us to simplify. The same thing, of course, let me show you. I think this you may want to see some real undefeated problem. This is 3-meter telescope. This project costs about almost $990 million project. And how engineers do this project? Actually, it would be interesting for you to look at the video of this project. $990 million project. Okay. Let me show you this kind of big project, big vibration engineering project.
Imagine yourself now in 2016 being invited to the opening ceremony for the 30-meter telescope, and let's imagine that you've been to see the 200-inch telescope. Well, the first thing that will hit you is, of course, it is a larger dome, but not that much larger. What is greatly different is that the telescope occupies a much bigger fraction of the dome, and the mirror is enormous, and it will hit you in the face because it's such a huge mirror. The mirror is 100 feet in diameter. The overarching theme for the 30-meter telescope is the history of the universe. It sounds simple, but really we're looking at understanding the origin of the universe, how galaxies like the Milky Way formed for the first time and assembled, how more complex molecules developed in space that leads to life forms. So it's a very grand but incredibly fundamental quest. The 30-meter telescope is a reflecting optical near-infrared telescope which has a reflecting primary mirror that's segmented with 492 individual segments that combine to make a 30-meter aperture primary mirror. The light is reflected from the sky to a 3.5-meter secondary mirror and down to a third mirror, which we call a tertiary mirror, which rather uniquely can rotate to reflect the light to any one of a number of instruments. On the 200-inch, we're talking about instruments of maximum weight, 1 to 3 tons, and here we're now talking about instruments that potentially 20 to 30 tons or so. The departure to a segmented mirror telescope was inevitable when we got up to the 8 to 10 meter class level. We would never be able to make a 20 or 30 meter single piece of glass. It would be extraordinarily difficult to support, and we wouldn't maintain the curvature over a very large area, and it would be impossible to transport. Probably the most challenging aspect of the 30-meter telescope is the correction for the blurring in the Earth's atmosphere. This is a technique we call adaptive optics. It's already in regular use on our existing telescopes, such as the Keck and Palomar telescope. And the way it works is we take the light from a reference image, either a star or a laser reflected off layers in the Earth's atmosphere, and use this signal to monitor the turbulence in the Earth's atmosphere. Now, the Earth's atmosphere doesn't behave in a very cooperative way. It's certainly possible to make this correction along one line of sight, but if you want to correct a cone of light coming through the atmosphere, then you need a number of lasers, each shining off different parts of the atmosphere to create a correcting signal that can be applied to recover the true resolution of an object as if the telescope was in space.
呢個最大嘅原因，點解 Facebook 嘅客翻嚟唔準同埋貴咧？好簡單啫。當大家用 Facebook 嘅時候，你有冇發覺你唔使輸入任何嘢？你只係睇下你平時你啲朋友。
So the question is this kind of thing. So that why we need to do this kind of very complicated vibration analysis, because how to say is all the optical system require you have minimized vibration. Otherwise, when you take a picture of this kind of either microscope or this kind of telescope, then you're big trouble to get a very good high quality image. So that this including our semiconductor industry want to do this kind of imaging of a nanometer transistor for your smartphone processor or CPU, so that all this kind of very precision engineering the kind of work of machine require vibration control, either passive or active vibration control. So this is one example. Okay, and so basically the key question now is this is why this vibration is a big trouble. It's so large, it's very big, and what happened? Based on what we learned in our previous all the chapters of the very large and the what? Your spin constant, the larger, and then what? Our spin constant inverse proportional to the length. While it's very long and then become very flexible. So this is something I told you that you need to understand about the basic all the previous chapters show you. You see this 30 meter. Oh, this long, huh? Right? And we already show you the kind of how the spring constant, effective spring constant, but how it's related to 3EI over L, huh? If you do cantilever being or something, so at least you see this kind of thing. So that probably here, L, length of this thing. So if this is 30 meter, so definitely 30 meter, and then definitely the longer than spring constant become very soft spring, become very flexible. So that the small external, this kind of wing or something, then can cause big problem to take a picture of the stuff. So this is a quite important thing, right? Yeah, for you to understand. Yeah. And of course, because this is very large, big machine, so that the frequency is small, right? We have learned about our natural frequency from the is what omega equals now k of m, right? So m is very small because L and mass very big, right? So that the whole system 1,700 tons, right? This is a big number and this is very small. So in this case, natural frequency, you can see, is a 2.2 hertz, very low frequency. Okay. Oh, they also include additional soil and foundation, so that there's additional thing, right? So this very big machine mechanic system on the ground and ground. In this case, a big mass, so we consider additional effective spring for the foundation. Okay. Okay, so here I show you that about how they really do the thing. Basically, they use this kind of undignified model, right? 18,000 node and 35,000 element finite matter, okay, to build. But nowadays, with your computer, this is not a challenge now. I told you, computer now, what's the typical memory in your PC? It can easily go to 1 terabyte. There's no problem. So that this has become piece of cake now. But in old day, right, 50 years ago or things, so that it's difficult. Okay. Okay, so that basically here I show you. Of course, the key problem is what? All this practical vibration engineering is what's the most difficult thing? Huh? So what's the most difficult for this real this engineering project? What's difficulty? Huh? I thought we already show you using sound mechanics. We can easily construct the N and K. Most difficult part is our C, damping. Damping is most difficult part for all this kind of real vibration engineering to prediction. You may need to use vibration measurement testing or make some assumption or look at some reference to see about what's typical value for this kind of damping matrix. Okay, so this is okay for this particular project. They try to give you some interesting assume. You see, 2% constant damping ratio based on some kind of DMM, the company, engineering company, the response spectrum. So this is it's a very big engineering company. So that assume 2% constant damping ratio. So I told you this really depends. Sometimes you may want to do vibration testing, or sometimes you try to get some reference, right? And then so that and this is especially for this particular one, it's very big and it's difficult for you to something, so that is another, I think, quite important thing. Yeah. Okay, so here you see, so they basically consider damping is one of most difficult part for all the vibration engineering. And the damping consists of damping in the base and soil damping, friction damping. Remember, there's a friction between those kind of bolt joint, right? And the cable, viscous damping due to the wind induced, right? and control system damping and structural damping, right? So that this is something quite difficult, I would say, in general. Structural damping, I think we will show you before, right? Chapter 3, Chapter 4, material damping, hysteresis, right? So that if you look here, basically a second hysteresis, right? F and K, so that yeah, Fx, okay, this is a okay. Anyway, so that I just tell you, so that we already the reason why we introduce this kind of basic concept is so here, so that again, structural damping, proportional vibration amplitude, right, and different damping level for different like earthquake, and then range from 0.25 to 2%, consider in for this particular TMT, this kind of telescope. Of course, this is in California. California do have earthquake. Okay, I don't know if you may look at some news. I think there's a one big earthquake in North Bridge in Southern California, right? And so the compared to Hong Kong, and then so that California, Taiwan, Japan, and some area in mainland China, Sichuan, they have earthquakes, so that when they do this kind of design of this large mechanical structure, the building, then this is something important to consider about this kind of now earthquake, right? Input in the design of the mechanical system. So this is something I think quite important. Yeah. And anyway, so I just show you this is anyway. So I can give you actually some additional reference paper on our Canvas website. For this, at least here give you one of I would say show you something practical case study of this kind of ending freedom the system. Why the N is not 1 or 3, it's N actually 35,000 elements, right, to really construct this kind of a model to do this kind of analysis. Okay. Again, do you have any question for this part? So that I should show you this is again. I do hope that you will find some of this kind of content would be useful. Why I know that some students may say, okay, they didn't have any background in this area, but that is I show you some of the real this kind of case study. Why that is something important. And then next one, if you have no problem, I need to quickly go through another part about the MCK. If we have if we have damping and how we look at this kind of damping in build this kind of MCK model for anti-freedom system. Basically, I show you in general there are two approaches, right? First is just like this TMT model. We make some assumption based on the experience here. In our TMT, this model basically is this one, right? So that try to get some assumption guess or estimation based on physical elasticity, or try to model the damping. So that this is a typical approach, I would say, in practical vibration engineering. So that here we show you one of approach called the model damping. Model damping, that means we already try to, if you are able to use, for example, our simplified method we described in this chapter, or FEM software, so we can determine M and K, right? And then try to do model analysis. So model analysis, in this case, we can find N vibration mode. Each mode will assume certain kind of damping ratio, normalized damping coefficient. So this is we call the model damping. And then once you're here, then of course we can easily do a transformation, right? We can get general solution for each vibration mode, and then convert into the physical space for each X1, X2, and then this is what we do. And of course, the second approach is second level damping. Second level damping is if we have MCK, how can we do the way to determine this kind of diagonalize N and K and C? So in general, it's not easy, right? So that the one approach in typical those textbook or even practical engineering, there's proportional damping or relay damping. Basically, it's very difficult. I can try to diagonalize N, K, and C at the same time. If there's no damping, of course, I will show you the vibration analysis eigenvalue. We can see if this is 0, it's easy. But so that's why. So that one idea come from Lord Rayleigh, right? More 100 years ago, the very famous physicist, right, in UK, and then I can what? I can assume our damping matrix N by N is linear combination of mass matrix and different matrix as R and beta are unknown. So that this is something quite important. That means proportional damping or relay damping basically is assumed damping matrix is combination, linear combination of N and K. That's and then alpha and beta can be partly determined by vibration testing. If you do some motion sensor, we show you smartphone sensor or some remote band, and then you get some vibration testing result, and then to estimate alpha and beta. So this is the approach. You see, once you this one, you can see it's very easy. We can show why this MCK can easily now based on our eigenvalue analysis, and then we have a way to get the model matrix, right? And then I can easily diagonalize this kind of MCK, right? So that this is something is much easier, right? For eventually you can show that so this kind of alpha this thing, right? In the each vibration mode, omega 1 with certain kind of eta 1, and then relate to alpha and beta and omega 1 square. So this is something, at least for fun, is a simplify our way to make this kind of undefeated MCK model for practical vibration engineering. Yeah. Okay, so that this is very important, and then I'll show you this is one of the important thing we introduce in this kind of thing. Okay, and I think we need to continue to go to the next chapter if you have no other thing. The next chapter is what? Basically, is what we want to show in part. If for some of problem we can go to vibration to what? N go to infinity. Oh, that's another simplified way. Maybe this is I quickly probably should only show one or two methods, right? And to show you that we are talking about sometimes engineers are lazy, and then we want to quickly to analyze this kind of very complicated product or mechanical system without solving very complicated equation motion wise. We don't want to solve this, and then in this case, can we quickly determine the net frequency vibration mode? So this is simply show you this approach. So there's typically there's a Rayleigh method, match iteration, and Dunkerville method. Why? These are widely used in vibration engineering in the many years when computer is very difficult. Why? 50 years ago, so that most of engineer has hard time to accept the powerful computer, and then so how can you simplify the way to do it? Is still thing. So here, Rayleigh method will show you in the beginning, based on the what? Energy method. What? Energy method basically we can show you. You see, basically, if your system have kinetic energy and potential energy, right, under harmonic vibration, I can easily show you determine our T maximum potential energy and maximum kinetic energy. And then with this kind of thing, and I can estimate our natural frequency most likely now in the simple way. So that is something I told you. We will show you this kind of thing. Basically, for undefeated model is more complicated, right? So that we have first one defeated we will show you in the beginning, right? For if an undefeated model, and then of course, actually, basically this is easy. If you still remember our one defeated. For one defeated, how can we use this very method? Huh? I mean, for each is 1/2, right? mv squared. And the harmonic vibration 1/2. V is what? V equals harmonic x dot. Harmonic vibration makes omega x. Right? So in case the omega square vibration amplitude square. And also V 1/2 kx. So harmonic vibration, we have 1/2 k here square. What is that? So in this case, under harmonic vibration, I can easily Tmax. Right? So make this two equal, and then I can solve omega. So this is for one defeated model, it's very easy. But for undefeated, then we need to consider about this kind of matching operation, right? But it's also not difficult to imagine, right? So basically, it's kx squared, you see? But this is a matrix, it's n by n. So this n by n here, okay? Oh, sorry, so it's not n, this should be vibration amplitude vector earning. This is the n by n matrix. So that in this case, we can easily do the calculation. So this method basically for undefeated basically is it's very easy. I just give this kind of a thing. Basically, you can assume certain vibration and then based on this kind of equation, I can easily show you about thing. Can quickly, basically, let me quickly show you example. What? For this freedom model, we show you. Basically, you can assume certain kind of x vector, and then using this kind of Rayleigh method, right? We assume certain kind of x vector, and using this Rayleigh quotient, and I can estimate this kind of a natural frequency without solving very complicated eigenvalue problem. Very simple matrix calculation. This is 1, 2, 3 is arbitrary, but you cannot try to make some extreme thing, right? So that this is a very simple way. Let me quickly show you in MATLAB. Okay, we define n, y, then we can assume our x0 is 1, 2, 3. Y, and then our Rayleigh quotient basically is y basically is k transpose multiplied by m x0 divided by n. So this is the Rayleigh quotient. Oh. Okay. So this is just show you about this kind of thing so that we can compare. I think very closure, basically we can compare about the, you see, so that omega square is 0.213 and then omega is here. So compare with exact solution, if we solve eigenvalue problem, so that it's a 0.4450. You see, this is without solve very complicated thing. We can get this kind of reasonable estimation. So that's why this is a practical and simple way to quick and dirty shortcut solution. Sometimes engineer is lazy, so actually you can easily show another example. If x is another number, what do you think? If x is, for example, x0 is 1, maybe 1, 2, 2, what do you think? Huh? It is 1, 2, 2, and then you can calculate here. You see? If you change our assumption by vibration empathy 1, not 1, 2, 3, 1, 2, 3, there is a 0.2222. So it's that means you don't need to have a very precise assumption about that the vibration amplitude, and then your natural frequency prediction using random method is still reasonable. That is something quite interesting for engineer, right? Like 60, 50 years ago, when computer is not powerful, and then I can easily do this kind of calculation. Yeah. So this is something I would say it's quite important for you to look at here. And of course, there's another practical approach, right? If in old days, if we have a real this kind of maybe some engine for a car with some gear train system, and can we quickly analyze the natural frequency of cars transmission system from engine to gear, so that using very simple approach, static problem you learn in solid mechanics, and then for we have three gears, right? And each gear we assume can contribute certain kind of loading and deflection, W1, W2, W3, so that this is a way now based on static deflection, and then we can easily try to determine our natural frequency without solving very complicated equation of motion. Basically, this kind of thing actually is related to what we learned this kind of radial method, right? So that once we have certain assumption in static deflection based on solid mechanics, right? I can determine our maximum kinetic energy, maximum potential energy, and try to make equal eventually omega natural frequency is square root of this G multiplied N1, W1, N2, W2, and this. Remember, W1, W2 is already what? This kind of deflection for static problem you learn in UG solid mechanics. Do you think? So this is something I think is very practical. Like many years ago, when our computer is not very expensive and not every engineer can access, right? And here I show you the real example. For example, you have a 3 rotor, maybe gears in a transmission in the car, right? M1, N2, N3. It's all given this kind of a mass and length. And then if you try to use this kind of, again, solid mechanics to determine this kind of deflection, we have talked about this many times, and then calculate the deflection due to M1. So it's a W1 prime and then location of M2 and M3, right? And then the same thing, we can try to look at the W1 double prime due to mass 2 and due to here, and then the same thing, eventually the total diffraction will be what? Due to this kind of diffraction due to M1 and 2 is here. Okay, so this is the static solution. Right, and then we can easily use this approximation to determine natural frequency. Okay, so that is I would say very simple way to show you we can quickly determine natural frequency of more realistic vibration problem. Okay, I think we run out of time, so I don't know, do you have any questions? Again, I do remind you that we want you to try to work on this kind of term project, so that if you I don't know if you have any question. Huh? Again, so that of course the first thing is still I think the key thing here is I hope you can try to look at this thing and then find about how you form a group, right? And then you try to think about some project you want to do. Okay. I noticed some students, especially MPhil students, they eventually try to withdraw the course. That's fine. I understand some MPhil students may be busy on their project and they withdraw this thing, but at least I tell you that it's fine. So that if you have any question, please try to contact me, and also maybe find some of students in to find the thing. Okay, do you have any question for the project? Okay, I think probably that